In this video, we are going to study the lock-free singly linked list, and it has roughly 3 variants, and we are going to study all these 3 variants in a uniform way. So let me start with explaining the memory layout of the linked list. Okay, so let me first start with writing the memory layout. Okay, as usual, this is a linked list that has a head pointer, and this head pointer is pointing to a node, and it has a value, for example 33, and then it has a next pointer, and also it contains the next node, for example containing 42, that is pointing to another node, for example 101, and that is pointing to the node pointer. So this is an example memory representation of a singly linked list that is also lock-free. So there are 3 operations. The first one is insert, and the second one is delete, and the third one is lookup. Insert is basically inserting a value, and deletion is deleting a value, and lookup is checking if the given value is present in the linked list or not. So we assume that the linked list is sorted. So if you are going to search for example, 43, you first look up the head pointer, read the 37, it is less than 43, so you move on. You go to the node 42, and this is also less than 43, so you move on. And you are reading the value 101, which is bigger than 43, so you immediately conclude that, oh, there is no such a value 43 inside this linked list. The reason is that I looked up all the values from the beginning to a node containing 101, but there is no value 43, and because this linked list is sorted, there is no 43 after the node 101. So even if this is not a node pointer, we no longer have to traverse the remainder of this linked list, because after 101 we know that there is no such a node. Okay, so far so good. And all these 3 operations has a similar implementation. You first look for the places where you are going to insert, delete, or lookup. You first traverse the head pointer and 37 and 42 and 101, and this is the point where you finish your traversal. So because 43 should be between 42 and 101, here you kind of know that, oh, this is the point where 43 should be there, but actually it is not. So we can insert 1, or we cannot delete 43, or the lookup result is failure. There is no 43 inside the linked list. So we can decide this kind of decisions when you look at this node. From 42 to 101, there is no 43 between these two, so we can either insert, delete, or lookup 43 accordingly. So all these algorithms are consisting of 2 phases. The first phase is traversing to the node. For example, here the node is between 42 and 101. And the second is doing the operation by inserting or deleting or looking up the value. So all these list operations are consisting of these 2 phases, and actually they share the same traversing algorithm. And there are actually three traversing strategies. The 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 oldest one is what is due to Harris, and another strategy is due to Harris and Michael, and another is due to Harris, Hurley. Oh, I am not sure of the spelling, but probably it is correct. Hurley Shabit. And as I said, there are three ops: insert and delete and the lookup. And it is basically there are three traversing strategies and three operations. So by combining this, we can get 9 combinations: Harris insertion, Harris deletion, Harris lookup, Harris Michael insertion, Harris Michael deletion, Harris Michael lookup, etc. So in the remaining of this video, we are going to learn the traversing strategy and how to perform these operations. So let me first begin with operations because it is a little bit easier to deal with because it is really easy. So for example, you found these two nodes, 42 and 101. So if you somehow figured out your value should be between a node and the next one, you can perform the operations as follows. First, for insertion, you can do that. So there are 2 nodes, and you want to insert a new node. Then what you do is that you create a node and then point its next pointer to the next block and perform a compare and swap on the previous node's next pointer. So that is basically what's going on in the insertion. If multiple threads are trying to insert the same node at the same time, it is okay because the KAIST will resolve the race condition. If your operation succeeds in the KAIST, then it is the case that your entire operation of insertion succeeded. Otherwise, if the KAIST fails, then your insertion is failed. And only one thread can succeed in casting the same next pointer. So that's the reason why, even though multiple threads are trying to insert at the same position, only one will succeed. And it is basically coordinating the multiple threads concurrent accesses. So this was insertion. And let's discuss the deletion. So how to delete a node? So for example, you are traversing this and you want to delete this node. And what you do is that you read the next node and you perform a compare and swap on the previous node next pointer. So by doing so, you can effectively removing the node inside here. But in order to synchronize with insertion, you need some extra care. So the reason is that if insertion and deletions are happening at the same time, maybe it is the case that you may lose an insertion. So suppose that in a linked list, you are inserting a new node here. So you can do that by performing a KAIST here. And at the same time, maybe another thread is deleting this node at the same time. These two operations may succeed concurrently. this is delete, and this is insert. So they are operating on the different locations. It is the next pointer of this, and this is the next pointer of this. And they can succeed at the same time, but it should not, because this insertion information is lost. Because the next pointer of this becomes this node, there is no, because after discuss, this node information is lost, and as a result, this node cannot be reached from the beginning. Effectively, you are losing the inserted node. Even though the insertion succeeded, this is not reachable from the beginning. That is the problem. So how to deal with this? So to deal with this, in the delete operation, you are first going to mark the next pointer as the logically deleted. So let me explain this with the figure again. So, okay. And in deletion, before doing a KAIST on this pointer, you are first marking this pointer as deleted by doing some fetch and OR operation. So after deleting it, you are going to delete, change this pointer value. For example, changing the least significant bit of this to 1. And only after this is succeeded, you are going to perform the KAIST. So this is the first operation to do for deletion. And the second operation is performing a KAIST here. And what is different from the previous operation? So in the previous operation, it just performed the KAIST on the first link without changing the second link. But in this revised implementation, you first tag the second link as logically deleted, and then you update the first link by changing it to the next pointer to the next pointer. And the benefit of that is that the insertion here and the logical deletion here, these two are now, this logical deletion here and this insertion here, so they are performing the read modify operation to the same location, the same pointer location, and as a result, they are coordinated. If the logical deletion performs first, then the node is deleted. If the insertion is performed first, then the new node is inserted. But they are not happening at the same time. If logical deletion is happening, then you cannot insert a new node because the pointer is changed. Your KAIST will fail. On the other hand, if an insertion happens before the logical deletion, then the logical deletion will fail because the next pointer is no longer the one you are aware of. It is updated to point to the inserted new node. So the coordination is done at this point, and the race is resolved between the logical deletion and the insertion in this next node's next pointer. So that's what's going on in this insertion and deletion, and they are their contention. And as a result, you just cannot perform KAIST in the deletion operation. You have to first logically delete the node by marking the next pointer as logically deleted. Okay, so in the deletion, you have to first mark this as logically deleted by tagging it with, for example, a 1 in the least significant bit, and then perform the compare and swap later. So let's say that this is the logical deletion, which means that even though the node is there, we have already logically deleted the node, and this is a physical deletion because we are actually deleting a node from the linked list. So logically, the linked list no longer contains the value if it is logically deleted. Even though it is not yet physically deleted, we know that we have to assume that this value is already deleted. So that's basically the protocol of this insertion and deletion. And lookup is very easy. Finally, we are discussing the lookup. And you can just go to the link and see if your value 43 is there or not. If the value is there, you found the value, and if there's no value, then you didn't find the element. So that's all, and lookup is easy. So please look at the synchronization between insertion and deletion. Probably this is the most interesting point of the lock-free singly linked list. So this will probably be asked in the exam. So please look at this. And now let's turn to the traversal strategy. So I said that there are 3 traversal strategies. One is Harris, and the other is Harris-Michael, and the other is Harris-Holy-Shabit. And now I'd like to explain these strategies in a different slide. Okay, so there are roughly 3 strategies. So I'm going to explain one in here. So the first strategy is Harris's strategy. So at the beginning, you are aware of the 2 nodes. So always you are pointing to the 2 consecutive nodes. And let's say that this is a prev and this is current. So far so good. And when you traverse, you are going to go to the going to read the next pointer here. And after one traverser, you are going to point to prev and current. So the original prev is pointing to the first node, and the original current is pointing to the second node. And in the next iteration, the prev becomes the original current, and current becomes the actual current at the next pointer of the current, and on and on and on. So if it is this is basically the normal case for all the traversal strategies. Harris, Harris-Michael, Holy-Shabit, they share the same traversal strategy by looking at the next node iteratively and moving what is called cursor to the next pointers, and on and on and on. But what is different among these 3 is how to deal with a logically deleted node. So for example, let's say that you read the next pointer here. You read the next pointer. And suppose that this is a logically deleted node. So this is, let's say that this is marked with 1 at its least significant bit. And you know that, oh, actually, this node is deleted. This node is logically deleted already. So we should not, for example, look up the current node, or we should not add a new node after this node, or we should not delete a node, the next node, by performing a compare and swap to the next node. It cannot be done in this way. Because this node is already deleted, we should not do that. So this is basically the meaning of this logical deletion. So even though there is a node in the linked list, you cannot do any operations on this node because it is logically deleted. That's the meaning of this logical deletion. So, okay, so what do you do? So in the Harris strategy, so we are going to, if you met logically deleted node, then you further traverse the new node, and you are trying to fix the list by physically deleting the node. For example, this is not yet logically deleted. Then suppose that this node is not yet logically deleted. Then what you're going to do is that you are updating the previous node's next pointer from the logically deleted node to the new node. So that is basically done by this Harris list. And if there are, so suppose that this is also logically deleted, and you traverse until you find a non-logically deleted node. So there can be multiple nodes between this prep pointer to the non-logically deleted node, and if you meet the first non-logically deleted node, then you're going to update the previous node next pointer to the first non-logically deleted node. So basically, when traversing the nodes in the Harris traversal, you're going to continuously fix the linked list by actually physically deleting the logically deleted node. So this is basically the Harris strategy. And Harris-Michael strategy is similar, but it is a little bit different. And what it does is that if this is logically deleted, then you're going to just fix the previous link from this to this, always. You're not going to update the multiple nodes at the same time. You are only fixing one node. You are only logically deleting. You are deleting only one logically deleted node physically. Only one is physically deleted by a single fix, by a cast of the previous pointer from this node to the next node. There's no such a way that the cast is performed on the next to the next node. It is not Harris-Michael. Harris-Michael only perform cast from a node to the next node, not next to the next node. So this is basically the Harris Michael strategy. So, okay, so far so good. And we covered the two strategies, and the remaining strategy is Harris, Hurley, Shabit. And what do we do? Even though in this strategy, even though we made a logically deleted node, we just keep going without fixing the node, without fixing the linked list. So this is usually done for an operation that should be executed fast. So if you want to traverse fast, then you can choose not to fix the linked list at all. So there is logically deleted node. That's okay. Just leave it there. You continue to traverse until you find a value. So that is basically the strategy of Harris, Hurley, Shabit. And it can be used for a fast lookup. If you don't want to fix the linked list for the others in your lookup, then you use this strategy. So these three are the three representative the traversal strategy that should be that is widely used for a singly linked list. And actually, these three can be represented uniformly, and that is what's done in the repository source code. So from now on, I'd like to go to the source code and read the lines by line by line. And okay, let's move on to the source code. And here is the source code. And in this source code, we are going to see the node. First, there's a node. And as usual, okay, I'm sorry. Okay, now you can see the code here. Okay, so node is, as usual, contains the key. But here we have key and value. So in the previous explanation in the drawing, I only drew the key, but in general we can design a map that is mapping keys to the values, and we can do that by storing both key and value in the same node at the same time. But in the previous drawing, I only drew a key for simplicity. But in this implementation, we have both key and value for generality. And this node is also having the next pointer. The next is an atomic pointer to the node. So that is pointing to the next node, basically. And also, a list is just a pointer, atomic pointer to the node. So far, this is very much expected from the memory layout of the linked list. So far, so good. And here are some code for creating a new list and deallocating the list. It is basically iterating through the nodes and dropping one of them. Dropping each of them. And here is cursor. That is basically an artifact for the traversal. I said that at each iteration of a traversal, you have to remember two pointers. One is the previous pointer, and the other is current pointer. And the purpose is that if you want to remove the current pointer, then you have to change the previous node's next pointer. And that is stored in this. And the current node is stored in here. So there are two pointers. One is pointer to the previous node's next pointer, and the other is the pointer to the current node. So at any point of time in the traversal, you are always you're always remembering these two data, and this two data is abstracted as cursor. So this cursor is the same cursor, the same word as the mouse cursor. It is pointing to something. Mouse cursor is pointing to somewhere in the screen, and this linked list cursor is pointing to some nodes. That's the reason why it is called cursor. So you can clone the cursor because you can traverse twice from the same cursor, basically. And at the beginning, the node's next pointer is null, and it is created by storing the given key and value. So far, so good. And let's see how to traverse a cursor. And cursor is at the beginning. So, okay, let's see this. At the beginning, there is a list, and you can create a head cursor that is pointing to the head. And the previous is the head pointer itself. The linked list head pointer is written in the cursor's previous. And then the current node is pointing to the actual head node in the linked list. So there are prev and cursor, and it is quite obvious that this prev is pointing to the current node because you just read from the head pointer here. And so far, so good. And if you get the head cursor that is pointing to the head node, and you can traverse using this cursor to retrieve a value. And as I said, there are three strategies. The first strategy is find Harris, and the second strategy is find Harris Michael, and the third strategy is Harris, Holihi, and Shabbat. And let's first look at this find Harris, and you are going to move on. So this prev next is going to be the current node, and you read the current node. You dereference the current node, and if it's the null pointer, then we are done because we finished traversing the entire linked list, and I know that I didn't find the value, so we want to look up the value, the key given here, but we reached the end of the linked list, so we didn't find the value. So that's the reason why this found can be false here. And after that, you are going to return the found value here. But before that, we need to do some cleanup. So that's the code for that. And let's now assume that we successfully dereferenced the current node. And the next thing to do is looking up the current node's the next pointer. So far so good. We know previous and the current node, and we are dereferencing the current node in order to retrieve the next pointer. So far so good. And now, if the next pointer's tag is non-zero, which means that the current node is logically deleted and its next pointer is marked with, for example, 1 in its least significant bit, and then we know that, current node is deleted logically. And that's basically what's going on in here. And what we do with this Harris list is that, the current node is now logically deleted, but we are going to continue traversing because we are going to delete it later. And for now, let's move on with only updating the cursor's current node. And let's point to the next pointer. So instead of pointing to previous and the current node, only the current node of the cursor is updated in this case. So let's see in the drawing that what is happening. So what is happening at the line is that, so this is Harris. So okay, and suppose that the prep was here and the cur was here, and we just figured out that this is logically deleted. When what we'll do is that just updating the the cursor's current pointer from the old node to the new one. So in this traversal strategy, it can be possible that the prep and current pointer points to faraway nodes if the nodes in between are logically deleted. And if this is also logically deleted, the distance between this prep and cur will be farther away. And we do that until we meet a non-logically deleted node. So that's basically what's going on in the source code. Okay, so far so good. And let's move back to the source code here. And we do that. We update the current node, current pointer, and begin from the beginning of the loop again, and on and on and on, until we know that at this point of time, we know that the current node's the current node is not logically deleted because its tag is 0, which means that it is not logically deleted. Okay, so far so good. If the last node, now you compare the current node and the key, and if the current node key is less than the given key, then you need to continue traversing because the value, the given key here, may be out there after the current node. So what you'll do? What you'll do is that you update the current pointer. You update the current pointer with the next pointer, and you also update the previous node. Previous pointer. It is the original current node's next pointer. So it effectively means that the new previous node will be your old current node, and your new current node is going to be your old next node. And you do it from again. So this is basically we are not finishing the loop, and we are traversing from the new previous and current node from the beginning. If the values are equal, then we are done. Then we are just returning the true here because you found the value. And if the current node's value is bigger, that it means that you didn't find the given key in the linked list. So you break with false, and the found becomes false. So overall, this found becomes true if and only if you actually found the value inside the linked list. So that is what's going on here. Okay, so now we see if the previous next is actually the current. It is the case that if the current node is not logically deleted. So if it is the case, then you just return whether you found it or not. Otherwise, you clean up by removing the logically deleted node between the previous and the current node. So let's look at the figure again. Here, you know that previous is here, and the current is here. Okay, let's okay. So that's the this is this and this are the previous and the current pointer from the cursor, and you know that they are far away. They are not adjacent. And if it is the case, you want to um, connect this to this by performing a compare and swap. So this is a way of fixing the linked list by removing, actually physically removing the nodes, the logically deleted nodes between the previous and the current pointer. So if it is compare and swapped and the logically deleted nodes are physically deleted, then it will help the other threads to efficiently traverse the linked list, because the logically deleted nodes are no longer present physically in the linked list. Okay, so far so good. And let's move back to the code. And here we are updating the previous next pointer from the current pointer. Let me say again. We are updating the previous pointer from the original next pointer to the current pointer that is far away from the previous node. And we are effectively physically removing or unlinking the nodes in between the previous and current node. And if we failed, it is okay because okay, so if it is successful, I know that the logically deleted nodes between the previous and current are actually unlinked. And if it's the case, we are going to destroy the unlinked nodes. Those between previous and current will be deallocated. But as before for queue and stack, you cannot do that immediately. Instead, you need to defer the destroy or deallocation of those nodes. The reason is that maybe concurrent threads are having a local pointer to the deallocated nodes, unlinked nodes. So you need to deallocate well after all these threads finished accessing the concurrent nodes. And it is basically traversing the linked list and basically marking those nodes as they should be destroyed or deallocated later after all the concurrent accesses are finished. And you're doing that for all the nodes between previous and the current node. And after that, you're going to return whether you succeeded in finding the node or not. So that's basically what's going on in this Harris search strategy. You search the value, and if there are consecutive logically deleted nodes, then you actually physically delete them. So in order to help the others to more efficient to traverse next time. So that's basically the Harris strategy. Okay, so far so good. And let's move on to the Harris-Michael strategy. And it is a little bit simpler. And it is the same that in the loop, you're going to read the current node and read the next pointer. And the next pointer's tag is non-zero, which means that the current node is logically deleted already. Then you're going to update the previous node. The previous node is updated from the current node to the next node. You should do that because the current node is already logically deleted, and you need to unlink it from the linked list by updating the previous pointer from the logically deleted current pointer to the next pointer. And if it is successful, you're going to default destroy the current node, which will actually deallocate this node when no other threads are accessing the node. And you continue by setting up the cursor's new current pointer as the next pointer and continue. And you similarly compare the keys and do whatever is necessary for for searching for the key. And what is important in this strategy is already present here. If you found logically deleted node, you immediately unlink it by updating the previous pointer to the next pointer. And you do that recursively or iteratively until you get the value, you found the value here. The last strategy is even shorter, and regardless of whether the nodes are logically deleted or not, you continue traversing until you found. So this is basically continuing traversal. And if you found the value, you check whether the tag is the found value for the found nodes is logically deleted or not. And if it is so, then you're going to return false, because logically deleted nodes are regarded as not present in the linked list, so you return false. And if it is not logically deleted, then you're going to true, because it is actually present in the linked list. So that is basically the three strategies that is present for the linked list. And there are lookup function. And after finding the right position for using these strategies, you can either lookup, insert, or delete. So basically, that is the what's going on here. When you insert, as I said, you insert a new node here. And in delete, as I said, we are going to mark the node as deleted by performing a fetch and OR operation. And furthermore, we are going to tag it as fetch and OR. And if the tag is already, if the next pointer is already tagged, which means that it was already logically deleted, then you are going to bail out and try from the beginning again. And if you successfully marked the least significant bit of the next pointer with 1, then you are going to perform a compare and swap on the previous pointer from the current pointer to the next pointer. So it is the same with the what was described in the board. So in the board, I said that the I said that in the deletion, you first need to logically delete the node by marking this with 1 by fetch and OR operation on the least significant bit, which is also RMW, to coordinate with the concurrent possible insertion. And only after that, you can actually perform a CAS on the next pointer. So you have to first logically delete and then physically delete later. So that is basically the order of the operations. And this order is reflected in this implementation. In deletion, you first mark the next pointer with 1 in the least significant bit, and then you update the previous node, previous pointer from the current to the next pointer. So that is basically the what's going on in the linked list implementations, and the finding for a linked list is basically getting the head cursor and find 1 and returning whether you found the value or not, and the cursor at the same time. And lookup means that you find it, and if you found it, then you return the value. Otherwise, you return none. And insertion is also simple. You search for it, you find it, and you found the value. Then you should not insert more values. So you just drop the value here, the credit node here. And also, if it is not found, then you need to insert into the cursor. So you call just cursor.insert. And if you succeeded it, then you return true. Otherwise, you loop again from the beginning. And in deletion operation, you find the key, and if the value is not found, then you return none. Otherwise, you delete the value from the cursor. So if it is successful, you return the value. Otherwise, you do it from the beginning because it is not done yet. And as I explained, depending on the strategies and operations, there are many combinations. For example, there are Harris lookup, Harris insertion, Harris deletion, Harris-Markov lookup, Harris-Markov insertion, Harris-Markov deletion, and this HHS lookup, HHS insertion, and HHS deletion. Depending on the traversal strategy and the operation you need to do for the linked list. So in this video, we studied the lock-free linked list and their operations. There are basically three operations: insertion, deletion, lookup, and there are three search strategies: Harris and Harris-Markov and Harris-Hurley-Shavit. So these all they are all fully combinational. So there are 9 possible implementation / operation for this linked list, and they all can be represented in a uniform way in like this. Okay, so far we discussed the algorithms and the synchronization scheme of the insertion and deletion and lookup. And in the next video, we are going to study why we need to put such orderings like release and acquire at this place or that place. For example, we are going to learn why this should be acquire, etc.